sponsored by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started. Good morning, good afternoon, everybody. I hope everybody's having a wonderful day. I want to welcome you on to the stream here today. So, let me know how you're doing in the chat. I'm definitely doing wonderful today, and now we're getting into some good stuff here today. Today we're going to be doing another big old bootcamp session. So if you're wondering where we are right now and everything, now obviously I got to put the hat on. That's sort of just the way this works, is I got to put the hat on. Let me get the hat on. Because that's the way the big old boot camp works. I got to get the hat on for doing the boot camp stuff, okay? There we go. Okay, there we go. So, anyways, I thought before we get started, I thought I would just run through a few things before we get into that good juicy stuff. So, if you're wondering what Big O Bootcamp is about, Big O Bootcamp is an essential toolkit. You could almost think of it like a complete guide. Well, or near complete guide. I can't claim it's complete because there's so many things out there that just simply people will not necessarily even need. But most certainly, what I'll be focusing on is you look at a lot of the essentials to allow students to be successful, especially when it comes to big O proofs, which is a very common exercise in second year or third year data structure classes. Typical. It's very typical. So often I like to provide all the complete tools to be successful when completing these types of exercises, whether it be just for like a test, an assignment, or just generally if you want to know actually how to prove this stuff and do it carefully. So, and in particular, I focus on the variant of the big O when it comes to its formal definition, which is very often where a lot of students have troubles at their first moments when they're taking this stuff. Because very often your first exposure to formal definitions is very limited, maybe to perhaps things you may have seen in calculus classes or some other maths classes, but you're not necessarily as exposed as often to this stuff in computer science classes, which you sort of get used to over time. But it's most certainly one of the first few kind of formal things you really run into, and you get used to the idea of, oh, I have to actually use this definition, so how can I do that? That's what we focus on here. So I'm not going to be talking about algorithm analysis here today. Instead, what I'm doing is I'm focusing in on how, if I give you some measurement, the complexity function of how many operations happen with respect to the input size, how do I determine that big O? And in particular, how do I formally do it? So that's a very important exercise to walk through at least once if you've not done it before. So in previous sessions, I focused on the fundamentals, so I'm not going through basic examples of big O claims here. I've done that in previous sessions. You can find those videos onto the YouTubes. So if you go to the YouTube channel, Page Wizard Games, Learning Entertainment, you'll find all the relevant information. By the way, whenever the chat pops up and all that stuff, it'll be popping around on the screen. You'll also find the links appropriately on the different portals that we're on, whether you're watching this on Twitch, whether you're watching this on Facebook, whether you're watching this on YouTube. You'll find all the relevant links in the description, or at least on the channel page. So the other element of this is that as we're doing this stuff, I'm making this stuff affordable and accessible to people. And that's a big part of what I do here, is I'm trying to make computer science education affordable and accessible to people. So you don't have to sit around and say, hey, Dan, do I need to go get some specialized, I need to get all of this stuff. I need to spend hundreds upon hundreds of dollars to get all of this extra training and extra understanding to enhance my learning? The answer is no. I offer a much more affordable option for such a thing. So that being said, you'll find appropriate links for these things, such as, for example, the Patreon, which has all sorts of different rewards. That's what helps make and produce my educational content, at least here on this channel. So if you find yourself curious about the notes after this, so I make all my notes available at least the supporter access, with the exception of certain series. The Big O Bootcamp is available at the general supports tier. If you go to patreon.com/pagewizard. But yeah, if you're wondering what I'm writing up here and all that stuff, all the notes, they're all available on the Patreon if you want to get yourself access to these. These are all going to be eventually put together into a book, which again, like I said, I like to make these things very affordable. So if you're wondering where all this is going to be going, it's going to be ultimately being put into one comprehensive guide if you're looking as a student or an educator in computer science to find ways to teach this stuff in a way that's easier to do than other alternatives that presently exist. Likewise, it's also going to be a rather comprehensive source, but it's also certainly not going to be it might be the ultimate, I don't know. I just tend to only know what I write and what I know about things and what people tell me. So that's why this feedback is really important. So whether you're watching now and you really enjoy this stuff, do let me know. Let me know in the comments, tell your friends, and of course, everything in between. So anyways, so keep in mind, these resources are things that students can use. If you just want to learn about computer science, this is great stuff. This is meant for everyone. So if you want to learn about computer science, this Big O, this is one essential element of how people describe algorithmic running time. So knowing a bit about Big O and how it works is something helpful to always have on the back of your palm. It's just sort of a second nature thing when you get used to it. So anyways, that being said, why don't we get started here? So we're going to get into this. But before I do that, I should remind you what the definition of Big O is, or at least the definition we're going to use. So normally I need to make sure I remind everybody about this. Let me just make sure everything's working out okay here. Just don't want to... Okay. I just have to make sure. So some reason some of my volume levels weren't on the screen exactly, so I wanted to make sure I quickly double checked. But anyways, by the way, if you have questions or comments or anything, or if you want to have fun, put it in the chat. I'm happy to look at it, or if you have questions, I'm happy to answer those questions. Normally when I start going through examples, normally I cover the example to its entirety, then I'll address specific things, unless it's something I could pick on the fly about. So just keep that in mind. Another element of this is to also have fun. That's always the most important rule, is to have fun, okay? So keep in mind, different platforms have all sorts of different mechanisms to communicate. You're welcome to use all of them. But yeah, no. So before I get into the session today, I'm going to go through a definition of Big O, so that way we'll all have the idea of what the definition of Big O is. And then once we have that, we're going to start talking about some properties that Big O has. Like I said previously, some basic example. Actually, maybe I'll do a warm-up example just to give us a flavor for this. So anyways, so I'm going to give you the definition for Big O. So that being said, suppose I give you two complexity functions, f and g. So just for those that aren't familiar with this, just as a reminder, a function, you can think of it almost like a machine, and, well, you can think of it as, it's a helpful way of thinking about it. Suppose I have a machine, it's called f, and it takes an input, or potentially many inputs, and it spits out output. So I could give it input, and it spits out output. That input, say in our case, will be the size of the input, or whatever that one input would be for our functions. And it spits out as output the resulting thing we call f of n. F is the name of the function, n is the input. For us, for complexity functions, normally this will be a positive integer. So those are numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc., etc. Start your counting numbers. F of n here will be a non-negative real number, meaning it's a number that could be 0 or anything higher that's a real number. So things like pi, 1/2, 3/2, 10,000, 10 billion, these are all positive, non-negative real numbers. So this is what a complexity function will look like, not physically, but it's an easy way for me to describe it to you. But I gave formal definitions for these earlier. in a previous session. So if I give you two complexity functions, say that one's called f and the other one's called g, then we say that f is big O of g. So note that this set theoretic in, it may be read as is in or is. Some people will just literally write is, or they may write this by convention an equal sign, but it isn't actually an equal sign. So we say f is big O of g if and only if. So for those that aren't familiar with this phrasing from logic, the way it works is that this is true if and only if, meaning that if this is true, whatever follows after this also has to be true. If this is false, then whatever follows after this also has to be false. It means that they're equivalent statements. So this is true if and only if there exists constants C, which is going to be a positive real number, and n0, which is a positive integer. So this fancy blackboard R means the set of all real numbers. The plus indicates that it's a positive real number, means it has to be strictly bigger than 0. This fancy blackboard Z means the set of all integers. Same idea. The plus makes it so that we're only talking about 1, 2, 3, 4, 5, 6, 7, and you're counting numbers. Just akin to something like before. N0 such that for all n greater or equal to n0, the following inequality has to be true for all n greater or equal to n0, meaning that there's going to be, if these two constants exist, this is going to be some point where if you plot this out everywhere after this or on that point, it has to be that this inequality is true. That f of n is less than or equal to c times g of n. So the output of f has to be less than or equal to c times the output of g. And this is what it means to say f is big O of g. So you may have seen plenty of examples before. If not, let me just give you some examples of how you might use this. So like in Big O Bootcamp, what we do here is we focus on how we can actually communicate and prove these things. So keep in mind that there's different styles for doing it. Just keep in mind that I'm trying to give you tips for how you can go about this in a complete way that would be reasonable at the level that you would normally learn this kind of definition. So let me give you an example. I said I wasn't going to do this, but I'm going to do it anyway because I think it's a little bit of fun. So here's a claim. Let's try proving that n plus 2 is big O of n squared. Now, for those that are acquainted with using big O as shorthand, you might look at this and say, Dan, you would say that that's big O of n, and that is correct. That is correct. That most certainly would be the smallest degree polynomial that would match what's on the left-hand side if you know how to use this thing. But I must stress that big O is, it's that dreaded M word, that it is a mathematical notation. So there's kind of two different things in play. There's the algorithmic description of the time complexity, and then there's this concept of big O, which has a formal definition that is flexible. It's an asymptotic upper bound. There's other kinds of asymptotic notations that do exist. I will cover those eventually. You might know these as big theta, for example. Big theta, for example, will prevent you from saying things like this. But you got to think of big O as an asymptotic upper bound. It bounds from above up to some sufficient amount by some multiplicative factor. It's always going to be that whatever the number of operations is for a given value of n, say the input, it has to always be bounded by some constant multiple of g. That's a sufficiently large value of the input. Seems pretty nice, right? So let's go through this. So one thing you're going to get cozy with today is I'm going to very often tell you kind of a game plan. Sometimes this will involve me giving you some intuition up front first, and then we get into it, or we go through it together. So here's the game plan. I want to use this definition. So what I need to do is, if I want to say that n plus 2 is big O of n squared, that means that, okay, this is f, this is g right here. So that means that I'm going to need to use this right here. There exists constant c is a positive real number and n0 that's positive real number, and n0 is a positive integer. I need these two constants. So that's the game plan. I need to find those two constants, and there's a lot of ways you could do it. I gave some strategies for doing this earlier on in a previous session. So you need to find them such that this is true for all n greater or equal to n0, where n0 is one of the constants and c is the other constant. So I'm going to go through just an example just so we get kind of cozy with this, because we'll be proving some more general properties that big O has. So we'll be going into this sort of as a bit of a warm-up. So consider this a bit of a warm-up. So today we're going to prove n plus 2 is big O of n squared. So what we're going to do is I'm going to try to find these two constants. I'm going to justify them to you rigorously. Means using that M word, the maths, the mayonnaise and mustard. Makes a good sandwich. We need to find those two constants. And once I have the two constants, then I can invoke this definition. I can say by the definition of big O, then it has to be that this is true, because I have those two constants, right? And this is the same as saying that. So that's our game plan. So I'm going to say we find constants, C, which is a positive real number. This stuff's really important, by the way. You don't want to be misstating what C and N0 are. Make sure your audience clearly understands what you mean by C and N0. C and N0 such that for all n greater or equal to n0, this has to be true, but I'm just going to put in what f and g are. N plus 2 is less than or equal to c times n squared. Okay, so now we have a very basic question, right? We need to find out c and n0. So what I usually do is, with a problem like this, I would normally start off by picking off c. Now there's a lot of different constant c's that will work here. I'm going to pick one that's relatively easy for me to argue with you about. I'm going to pick c is equal to 3. And I've given reasons why I might pick this in the past. I use what we call the look-alike approach. So what I do is I try to make these n squared terms match up with terms that are on the left-hand side, but by mimicking them. So for example, I have one n there, and I have I just have 2 here, right? So can I rewrite this in terms of n squared terms? But obviously, whatever has to be on this side has to be at least as big as whatever each one of these terms is on the left-hand side. So for example, okay, I have one n and I have this 1, 2. Okay, if I could write this as n squared and a 2n squared, I can say, okay, n has to be less or equal to n squared, and 2 has to be less or equal to 2n squared, right? So if you combine those two statements, those two inequalities together, then you could get this, which is what we're going to do. This is one way you could do it. There's several other different constants that work, but this is a pretty easy way to justify it. Pick c is equal to 3. Then we find n0, so that n plus 2 is less than or equal to 3n squared for all n greater or equal to n0, right? So now I've just filled in one of the blanks. Now I need to find the other constant. So now I'm going to do what I just said. I'm going to make a look-alike by forming a chain of inequalities. So when I have those chain of inequalities in place, I'm going to justify it by combining the terms, by adding them pairwise. So you'll get to see what I mean in a moment. And then when I lump them together by summing over the inequalities, I should get what I've chained together. So watch this. This is a really key way of arguing this. So I call this the bucketing approach in a previous session. So here we go. And we find n0. So now I'm going to make an observation. But I might remember, the reason that's coming up is going to come at the end of this statement. So if you don't like the way I framed it this way, another way you can frame this is you can talk about the two separate inequalities first, say sum over these two inequalities, then you get this. That's one way you could do it. I'll just write it this way just for the sake of consistency with how I've done it before. Observe that for all n greater or equal to 1, that n plus 2 is less than or equal to n squared plus 2n squared, which equals 3n squared, as the following has to be true. So what I do is I take each one of these terms and I compare them. And then I sum over those two separate inequalities after I compare them. Since the values of these never go down, they always go up, then lumping them together only makes bigger numbers, right? And the whole idea is that if I have this is less than or equal to whatever's on the right-hand side, for each separate term, when I add over each inequality, as you're going to see, then it means that it has to be true for over the entire inequality. So, as n is less than or equal to n squared, if you're not convinced by this, divide both sides by n. As n is less than or equal to n squared for all n greater or equal to 1. And we can see that 2 is less than or equal to 2n squared for all n greater or equal to 1. So notice that I'm giving you a justification for why this has to be true. So notice that I have this one here and this one here. Now, if you don't like this explanation, you can easily just say, as by summing over the following inequalities, these two, both are true for n greater or equal to 1. And that's how you get this right here, right? So now I have to pick n0. And now notice that all of these inequalities are true for n is greater or equal to 1. So I'm going to choose n0 is equal to 1. And keep in mind that I could have picked n0 is equal to 2, 3, 4, 5. It wouldn't make any difference. I'm just picking one that follows from the reasoning I gave. That's a very important detail here. So I choose n0 is 1. And now I could use the definition, right? I've gotten the two constants. Therefore, by the definition of big O, then we know n plus 2 is big O of n squared, and we're done. And I put the box there to indicate the end of the proof. Piece of cake, right? We did examples that were tougher than this before. But yeah, if there are any questions, feel free to put anything in the chat. If you want to bug me about anything, happy to chat about it. So, anyways, so this is just a warm-up just to get familiar with the definition of big O. So I thought it'd be a good idea I did this so that we could start talking about properties that big O has. So I'm just going to erase this, and then we're going to start the session. So it's just a bit of a warm-up. So you're going to get very acquainted with this definition of big O. So I must stress that the list of properties we're going to talk about today is not a complete list. I may go in the future, come back and revisit this topic again. But I'm most certainly going to be focusing in on some of the main ones that you might encounter, or at least if you're curious about the proofs for them, I provide some proofs here. So I give you an idea of how and why they work and exactly what you could say about it. So anyways, let's get in on this. So let's get in on this. So in this next part, we're going to be talking about properties of big O. So in particular, we're going to be talking about how we can prove those properties. So I'm going to describe a variety of different properties that big O has. And we're going to see how we can prove those statements using the definition of big O. So many of the techniques I've shown you in the past will be very helpful here too. So you're going to find that a lot of the ideas and sketches for these proofs very often rely on your intuition for how you can prove basic big O claims. But here's the catch though. This is the big catch. These claims are going to be about arbitrary complexity functions. So they're not just, oh, n is big O of n squared. It's not a claim like that. It's going to be that, oh, I give you two complexity functions. You don't know what they are. They could be arbitrary. So they have certain conditions they may have, but the point is that you don't know what fixed complexity function they exactly are. So we're going to talking about a variety of these. So you're going to find that a lot of the proofs I'm going to give you almost operate like a blueprint or a skeleton for how you might prove other big O claims. And sometimes you can even apply it to simplify down some claims. For example, in a previous session, I've talked about the idea that the transitive property of big O can be used as a shortcut in some of the proofs I've shown you before, for example, in smoothness. So, here's the first claim. So, what I'm going to first talk about is that big O is reflexive. So, it has what we call the reflexive property. Now, you may not have ever heard of this term reflexive before. Here's what it means. Given any complexity function f, you could say the following. You could say that f is big O of f. So if you've never heard of this term, and you might ask, why is it called reflexive? Well, I like to almost look at it like you're looking at a mirror. So if you have the thing you're studying, and you ask the question, does the thing have the property? That's what reflexive usually means. So if I'm looking at the mirror and I'm asking, do I have the property? In terms of big O, if I give you a complexity function, the answer is yes. So I could just say, for example, that n is big O of n. I could say that n squared is big O of n squared. I get that for free from this property. So we're going to prove this next, and I will tell you up front that it's going to be probably the easiest proof we're going to do here for the properties. So the first thing you need to know is that we're dealing with a statement about any complexity function. So normally when we phrase a proof like this, we need to make sure that we're talking about any complexity function f. That's the first thing I need to point out, that the length is a little bit different than just any one fixed complexity function. So I need to kind of pin one down, but I'm going to give it a name. Consider any complexity function f So if I want to show that f is big O of f, what should I do? Well, what did we do last time? Well, what we did was we used the definition of big O, right? That's one way you could do this. So naturally, I'm just going to use that. And what's the game plan? The game plan is to find the two constants c and n0, right? So if I can find those two constants, then I can invoke the definition of big O, and then we're done. That's going to be about as simple as it gets here. So then, to prove the claim, we find constants c, which is a positive real number. That plus is getting a little long for my taste there. And n0, which is a positive integer. So that for all n greater or equal to n0, it has to be that f of n is less or equal to c times f of n. Well, but here's the catch here, right? We need to write it out like this. Sorry, I'm getting really excited here. Well, the minute you write this out, you see f of n is less or equal to c times f of n. What's the easiest constant I could pick here to make it so that this is in fact equal? So what can I do to make this a little simpler for myself? Well, what I can do is I could just assign C to be 1, and then I have f of n is less or equal to f of n. And you know the left-hand side has to be equal to the right-hand side because it's both. It's the same thing on both sides. So this should remind you of some of the first examples we did. So I'm going to pick C is equal to 1. Then you observe. Then observe both sides of the inequality are equal. Implying f of n is less than or equal to f of n holds for any n greater or equal to n0. Remember, n0 is just some positive integer, right? So all you have to do now is you just kind of tip this over. You just pick n0. You can pick any n0 here and it works. So I'm just going to choose n0 is equal to 1. Therefore, so if you find yourself looking at this and you're like, for any n greater or equal to n0, now you know n0 is a positive integer, right? Now if you're really just like, okay, Dan, but I want to really put a number here, you could just put 1 right here and that's perfectly fine. It's easy enough for you to convince somebody that two things that are equal on the same sides, that it will be that it doesn't ever differ, right? Because it's an equality. It's an equation. Therefore, it's not just they're not going to differ in their values. Therefore, by the definition of big O, so now I just pull out that big O definition, we can say that f of n is big O of f of n. And we're done. Piece of cake, right? So big O is reflexive. So just to remind you what that means that like n is big O of n. So you don't have to like, this property says that, yeah, you basically just say this. And the proof gives you the y. So notice that this explains to you, it's not an explanation, it's actually an argument. It gives you the y. So you can think of it like an explanation, but it's a formal argument, right? So if anybody asked you, well, why is that the case? We could just show them the proof, right? So in fact, if you gave me any claim of like n is big O of n, or n squared is big O of n squared, you could just straight up use this proof and plug in your functions and it should work. This is how and why, when we get a general statement like this, you should be able to just use this as a blueprint for any such claim. So if I give you n squared is big O of n squared, because this is for any complexity function f, all you have to do is you should be able to just say, whoops, I see this extra parenthesis here. Sorry, there's a little bit of fun there. You just put n squared here, and you just put n squared everywhere you have f of n, or f. You just put n squared everywhere, and this should all work. So anyways, that's the reflexive property. So I don't see any questions, so I think I'll proceed to the next property. I think this is a pretty darn straightforward one. So I'm thinking the next property we're going to talk about is the following. And this is one that comes up all the time when you're doing analysis. Constants independent of the input do not matter. That's kind of the summary version of what I'm going to write. So constants independent of the input do not matter. So what am I saying? And keep in mind there's several different ways you can reformulate this property, and it will still probably be true. It works like this. So what I'm saying is if k is a positive real number, and you know that f is big O of g, then it also has to be the case when you multiply k by f. Sorry, I'm getting very excited about my f. That's a little bit of a wide side there. K times f has to also be big O of g. So what does that mean? So if you're talking about something that's a multiplicative constant like this, and you know that this is just some constant, it doesn't relate to n at all. But if you just find out that f is big O of g, then it's no different than if I just, like, it follows that it also has to be the case when there's a constant in place. There's several other ways you could reformulate the same statement. This is just saying that the constants don't matter. That's what it's essentially saying here, is that you get this if you know that's a constant and you know f is big O of g. You could, like I said, you could also rewrite this in several other ways too. But this is the way I'll present it to you. So here's a proof. Now, notice that this is actually a conditional statement about two arbitrary complexity functions and also a constant. So you have to keep in mind that often if you're not sure about how to start with a proof like this, you can start off by writing out, like, consider any k, f, and g with the appropriate domains in place for them. But what I'm going to do is I'm going to take advantage of the fact that I have this and this being true to follow this statement. So remember, this is a conditional statement. You can think of it like a logical test. So you might know this, like, say in programming, you might know of an if statement. So what you might say to yourself is, Dan, if this and this are true, then it must be that this follows, right? So all I'm going to do is I'm just going to take these two and say, hey, look, if this and this, then it has to be that this is the case. That's what we're trying to prove here, right? So I could take these in my proof as givens, and I can use them to deduce the consequent of our conditional statement. So that's where I'm going to start here. As f is big O of g by the definition of big O, by the definition of big O. So by the definition of big O, we have the following, right? It means we have those two constants, right? We can use them. So for those that are inclined for fancy terminology, if I give you a statement like this, what it really is saying is that I get those two constants for free, right? That's what it's saying. So we call this an existential instantiation when I want to use those constants, because this is actually a statement that talks about the existence of certain constants such that the inequality is true for all n squared equal to n0. So if I know this is true, then it means that I can instantiate, almost like I'm declaring variables, those and give them names by the definition of big O. So I'm going to give them names. There exists C prime. I'm not going to call it C and N0. I'll call them C prime and N prime. Like I said, I can give them names. So C prime and N prime, which is a positive integer, so that for all, remember, all I'm doing is writing out the big O definition now just for f and g. For all n greater or equal to n0, it has to be that f of n is less than or equal to c prime times g of n for all n greater or equal to n prime, right? So now we have this. So we can use this information. Now, because I've laid this out, now keep in mind I didn't have to state this first. I could have stated it after this. What I'm now going to talk about is what I'm going to do to ultimately prove this claim now. So we're just as usual, I'm just going to say what I'm going to do, the game plan. We find constants. C, which is a positive real number, and N0. That N0 is looking a little too much like a no. I'm going to need to fix that. N0, which is a positive integer, so that for all for all n greater or equal to n0, it has to be that f of n, well, in fact, it's not just f of n, right? It has to be that it's k times f of n is less than or equal to c times g of n for all n greater or equal to n0. So that's what we need to do next. So I got some ideas here. Now remember, I have a constant called c prime. And that comes, so I know f is big O of g, so it means that I already have a couple of constants I can play around with, right? So the idea here is I'm going to pick those up, and I'm going to try to make it so that I can still scale the left-hand side. So notice it's k times f of n. I'm going to try to scale the right-hand side so it matches the fact that I'm making the left-hand side k times bigger. So this is how I'm going to go about figuring out the constants, okay? So remember that k is a constant. K is a constant. It's not, has nothing to do with f. This is going to be important for our reasoning here. So I'm going to say that as k is a positive real constant. It's important that it is a positive real constant, by the way. It can't be 0. You would have to do a little bit more massaging to make this work if that were not the case. We're going to pick C so that, remember, I'm going to try to make it look alike the left-hand side. So what I need to do is I'm going to make it so that I can get rid of the K on the left-hand side. So I'm going to try to put K somewhere in here. And then I'm going to try to multiply it by something that I know for a fact has to be true. So notice that if it's K times G of n, then I'll have K times F of n is less or equal to K times G of n. If I divide by K on both sides, then I end up with F of n is less or equal to G of n. But we know that actually isn't true for all n greater or equal to n prime, right? So you need to actually incorporate the constant that I have up here. So I'm going to pick that constant. So I'm going to pick C as follows as K times C prime. Then we find n0 such that K times F of n is less than or equal to C times G of n, which is going to be equal to K times C prime times G of n. And now remember, as I said before, K is a positive real constant, so it means that we can divide by K. So I'll say constant K is a positive real number. You should write the full word number here. I'm just doing this for the sake of brevity here. So by dividing both sides, of the inequality, by K, we end up as follows. So I'm just going to write it over here, okay? So as I've sort of laid out here, is we know that we already have something that works. So why disrupt that? So we're just trying to pick the constant so that we could just massage that into our statement that we're trying to prove. Which shouldn't be very much a surprise or anything like that. At least we got a little bit of a feel for this. So after we do this, remember we're going to have K times F of n is less than or equal to K times C prime times G. Which this, if you divide by K on both sides, this is no different than me writing as follows. F of n is less than or equal to C prime times G of n. But what's this? Well, we already show that that is actually the case, right? We already know that this is true for certain values of n, which holds for all n greater or equal to n prime. So what should I pick for n0 then? Well, I should pick n prime, right? Choose n0 is equal to n prime. And then now we have two constants. Now you might ask, Dan, these are for arbitrary functions, and you didn't specifically give those like numeric values. So like, how do you know this actually works? Well, it's remember, the way the logic works in this statement is that if k is a positive real number and f is big O of g, you know that those two statements are true, right? So it's going to be that it follows from those two things. So you know you're going to have those two constants for this to work. So if you have those two conditions in place and they're both true, or at least they're going to be the case, then you should be able to plug them in appropriately here. So like I said, these are a little bit more general statements. So now I just conclude the proof by, of course, invoking the definition of big O, because we need to do that. Remember, you find the two constants, right? They're like, imagine you have like a barrel here, and you're trying to find those two constants. So far I've done that. I've justified the two constants for you. I picked them, I have them in my hands. Now I need to present them to you and say, here's the conclusion. But I use the big O definition to do it, right? Therefore, by the definition of big O, we know k times f is big O of g. And we're done. So those constants independent of the input, they don't actually matter in terms of big O notation. In practice, they might. So I must stress that those constants, they're great to suppress when you're talking about general instances of your problems, and if you want to talk about this in a machine-independent manner. However, remember that still, when you're counting operations and all this stuff, or if you're timing things, those details do get lost sometimes in big O notation. I'll give you one basic example of this. I won't include this in the notes here, but one example I can include for you is that if you ever heard a polynomial evaluation, so imagine you have a polynomial. So we've talked about polynomials before. Suppose I give you a polynomial, and I give you an input x. So suppose, just as an example, suppose I give you something like this x is, like say if it's ax squared plus 1 or something. Where a is some constant. Actually, let's just like 2x plus 1. Say if you have all the coefficients as well as part of the input, like if it's given to you as an array, you can compute or evaluate this right here by just simply naively going through each one of the terms. That would be the coefficients that you're given. So these would be the coefficients that are provided as part of the input for your algorithm. Each one of these it yields a naive evaluation of the polynomial. If you compute the big O for this, it'll actually be no different than if you compute it with a more sophisticated technique, something called Horner's method. If you employ Horner's method, which actually does less multiplications, it does about half. The big O in this case is actually the exact same as the naive one. Both of these actually yield the same big O for their time complexities. But the thing is, the big O will actually suppress those constants, the ones we were talking about here. So in this case, you can see that sometimes those constants actually matter. So that's more of a consideration from another standpoint. Right now we're focusing in on trying to prove something is big O. But these are considerations you have to make when you're analyzing an algorithm. So, for example, if you really care about those multiplications, maybe count those separately. And maybe even consider them as a discrete thing you actually want to count and isolate so you can present that to somebody. Or you can just make your model more precise about these things. Say, make those multiplications actually something that's a bit more expensive. But yeah, no. Are there any questions about that? Pretty interesting stuff, right? This yields one of those basic rules that you know about from Big O if you've ever heard of these kind of shorthand rules. We've talked about them before. So, if we're okay with that, I'm thinking we'll get to our next thing we would like to prove. Let me just erase the board here. Give it some space here. Now, while I do that, I'm going to get the chat up here. So if anybody, I heard somebody earlier potentially follow. Unfortunately, those notifications don't come out on the stream until I pull up the chat here, because I usually don't want to have it disrupting the example as we're doing things. But yeah, no. So what I'm going to do is I'm going to erase the board here. Then we'll get to our next property. And here's the neat thing about this next property. Is we often very much use this. Like, it's all like when you talk to computer scientists and you talk about Big O. You know, when we talked about like, oh, well, we know like if I have a bunch of things that I'm doing, like, oh, this is a linear time operation, then I have a quadratic, then I have another quadratic, then another quadratic number of operations. You know right away that it's all going to total up to some quadratic number of operations. Very often we use this all the time. It would like to have some way of actually just being able to express this. So also one thing I will mention is that in the notes, I'm going to include a generalization of this proof that generalizes to d complexity functions as opposed to just 2. I do actually have a video on the channel that actually goes through this proof if you're curious about it. You'll probably have to find it. It's another Big O Bootcamp video. But it's a generalization of the max rule. I swear I had... Where'd the max rule go? I think I mixed... Yeah, that's it. Yeah, I have it here. Never mind. We're okay. I thought I was looking at something else at first. It's just one of those days today. So anyways, let me erase the board here. So keep in mind, let me know how you're doing in the chat. Hope you're having a beautiful day so far. I know I'm having a blast here. Hope I can give you a little bit of my energy if you're just really feeling bummed out today. Let me just get a few things out in front of us, because we're going to need a few props for this. Well, I'm going to need some props for this to explain this properly. Let me just get that out of there. Okay, I got the board erased. I'm going to erase that board over there as well while I'm at it. But let me know how you're doing. If you have any questions, remember, if anybody's hopping on in a little bit later, feel free to put your questions in the chat or in the comments. I'm really happy to answer any questions. I'm here to help. Just getting the boards nice and clean for us. So that way I don't have to interrupt us in the middle of this. Okay, so I don't see any questions, so we're going to just kind of proceed to our next example. So we're going to be talking about another one. So some might call this the max rule. I'm going to call it as follows. So this is the next property we're going to talk about here. Like I said, some people call this the max rule. Take the largest function over functions in a sum. So what do I mean by this? So given any two complexity functions, and I must stress that the statement is rather general. So functions f and g, then we can say that f plus g is big O of the max of f and g. So I'll explain what I mean by this in a moment here. So f plus g is big O of the max. That M is looking a little excited there. The max of f and g. So what does this mean? So if you're not familiar with the max function, the way this works is that if I give you some value for this function here, if ever I have some input of a sufficient value, so if I plug in a value like say 1 or 2 or 3 or 4 or 5, it'll take whatever the largest is of the values among them. So very often the way this max function would get used in this context is that if, say for example, f is n and g is n squared, then this means that all of this will be n squared. So it collapses into that. So you might ask, Dan, why would I want to care about this property? Now, very often when we analyze algorithms, not always, most certainly there's more delicate cases you have to be considerate of, is very often you have kind of parts to your algorithm. Say you have like the first part. I give an example kind of like this. So you have the first part, the second part, and the third part. And say you know that the first part is something like, I don't know, like n. Say the second part is n squared plus 2 or something, many operations. And say the third part is, I don't know, actually we'll stick with just 2 for now. I'll make a remark about multiple ones. So say if I have 2 of them here, keep in mind you can always group them too. Say if I have 2 parts to my algorithm, the first part does some linear number of operations, the second part does some quadratic number of operations. What this rule is saying to you, this max rule, is saying to you is that if you take the sum of these, so suppose that these are the total number of operations that happen in your algorithm, for example, it doesn't have to mean that, then what it's saying is you take the max of f and g and you get that in terms of big O. So in this case, notice that you have n squared plus 2, so you could just simply say that this sum over all of these is big O of n squared plus 2, which more simply is big O of n squared. Okay? So this is what we're going to prove here next. So ultimately what I'm saying is that if you take the largest function over a sum of 2, then you're going to have it where you're going to end up with the largest one at the end for the big O. So we use this all the time when we count up operations in big O. When we're computing the big O for an algorithm when it has multiple parts. So what we do is we do what we usually do. So keep in mind you can say arbitrary complexity functions, but here I'm just going to cut right to the chase. So suppose that we have 2 arbitrary complexity functions, f and g. I'm just going to cut right to the chase, just to be clear. We find c and n0. Which remember, that's a positive real number. This is a positive integer. Such that for all n greater or equal to n0, we know that f of n plus g of n is less than or equal to c times the maximum of f of n and g of n. So what I'm saying here is that if I take the sum of these, it has to be less than or equal to c times whatever the larger of these 2 values will be for a given value of n. So anyways, you might ask, Dan, how are we going to pick the constant? And that's a very natural question, right? Well, I like to think of it in the following way. So let's think about this. Suppose that I had one function from this box, and I have another function from this box. And I want to claim that if, say, whichever of the 2 functions I take is big O of the max of the 2, it doesn't really matter a whole lot if one function is much smaller than another for a given value of f. We could just take whatever's the bigger of the 2, right? But here's the thing. That's what this says, right? So this is saying that I have f plus g. Now imagine that f is less than g. then you know that this is going to be less than, like this sum is going to be less than or even less than or equal to g of n plus g of n, if that's the case. And you can think of the other case too, where g is less than f for certain values of, well, for sufficiently large value of n. Then you could say the exact same thing just in reverse, right? So you could say that, okay, well, that means that f of n plus g of n is less than or equal to f of n plus f of n, right? The point here is that there's two of them. So all I'm doing is summing over two, but each one always gets to be the bigger of the two. So a very natural selection for C will be 2. Why? Because I'm summing over two things and I'm always taking the larger of the two things. That's the intuition here. But we need to actually check that. Just saying that it seems right isn't enough. We need to actually verify this. Then we find n0. So that for all n greater or equal to n0, we know that f of n plus g of n is less than or equal to 2 times the max of f of n and g of n. Well, like I said, we can always fudge around with what f and g are by just simply taking the larger of the two. So I'm going to take our bucketing approach and I'm just going to extend that to just this case. So watch this. Well, for all n greater or equal to 1, both of the following inequalities are going to be true. Both f of n is less than or equal to the max of f of n and g of n, right? This has to be true, right? Because f is included in that max function. So if g ends up being bigger than f for values of n, where n is greater or equal to 1, it'll pick g, but if it's bigger for f, it'll pick f. So you're covering your bases when you say something like this. And g of n, for n is greater or equal to 1, that's important, is less than or equal to the max of f of n and g of n. Same reasoning here. So now all I'm going to do now is I'm going to sum over these two inequalities. So I want something that looks like f of n plus g of n. Here's f of n on the left-hand side, and I have g of n on the left-hand side. So if I sum these two inequalities, I should get something that's very nice for us. So let's head on over here. Let me just take a little walk. We can all walk, walk, walk. And let's head on over here. So that's exactly what we're going to do. So for every n greater or equal to 1, we know that f of n plus g of n. So if you really want to get more precise about where this comes from, you can just point at those two inequalities. So this is something that you can do, is you can always make, like, put a star beside that inequality, and this inequality put like 2 stars or something beside it, just to indicate what they are. So for every n greater or equal to 1, by summing star and 2 star, you get this. But I think that it should be nice and flow from this way as well. Is less than or equal to the max. And that's, my curly braces are sort of a little sad, but that's okay. They're my friends too. Plus the max of f of n, g of n. So remember, this is what it says on that first inequality. F of n is less than or equal to the max of this. G of n is less than or equal to the max of this, right? That's what we said just a moment ago. But what's this? It's just 2 times the max of f of n, g of n, right? Which is exactly the right-hand side. There's nothing arbitrary about this if you just understand this bucketing approach we keep using. It's a feature. It's very nice. So I'm just going to make this a comma. So I'm going to choose n0 to be 1. Because this inequality works for all n greater or equal to 1. So now I'm just going to conclude our proof by invoking the definition of big O, and then we're done. Therefore, by the definition of big O, it has to be that F plus G is big O of the max of the two. And we're done. I'm going to put a end of proof mark right there, and we're good to go. But yeah, no, so this is how you can prove this claim. This is one way to do it. One thing I do want to make a remark about this is that in a previous session, we talked about how we had this property that we have for polynomials. And you know how I talked about, oh, you just sum up the coefficients of the polynomial using absolute values on each one. And I gave you a proof for this. Now, you might find it interesting that actually you can generalize the max rule that I have here so that you have d complexity functions, and you're allowed to have it so that each complexity function has its own coefficient. And you can actually adapt a technique very similar to the one that you talked about when we talked about polynomials there. So if you have the max rule, it's like say if you have this max rule in place and you wanted to put coefficients on f and g, you'll notice very quickly that the way I picked the constants depended on the number of terms. So do you see that if suppose, for example, I have 3 terms or 4 terms or 5 terms, I could just simply pick the constant to be whatever how many terms there are. Likewise, I could introduce coefficients to each one of the functions and change them to those, and you'll see very quickly, if we use this max rule appropriately over d complexity functions, that you can actually generalize this rule so it subsumes the max rule and also the polynomial, the way you can handle a polynomial that I talked about previously. So I'll have that property discussed in the notes, but I'll write it here, okay? So I'm going to write it here just for the sake of completeness, but the proof will be in the notes. So here's a generalization that you can take to go even further than this. A generalization. So given d, which has to be a positive integer, it can't be 0 or negative for some reason. I don't know what that would make sense of being. Suppose I have some positive integer number complexity function, so d is a constant here. So what I'm claiming is that if you have d of these, suppose I give them names, f of 0 of n, f1 of n. So keep in mind, I'm just writing I'm saying the of for you to understand what I'm writing. And this goes up to f of d of, so d minus 1 of n, and you have coefficients. And coefficients, a0, a1, all the way up to a d minus 1, which is going to be, these are all going to be real numbers. What you could do is you could actually prove the following. And this is the generalization of both the polynomial case and also the max rule. So it's actually the combination of both, and it actually takes techniques from both of these. So if I have sum from I is equal to 0 to d minus 1 of ai times fi of n. So if I sum over all of these coefficients multiplied by each complexity function, it has to be that this is big O of the max, where you consider the max over all the complexity functions. So this is a generalization of the max rule over here. So if you make all the coefficients just 1, you'll see very quickly that it's just the same idea we had over here, just when you have it when d is equal to 2, right? So also, you'll notice that it should give you shades of the polynomial type of setup, is where you have d is equal to, I believe it's k plus 1, if I'm thinking offhand here. And then you just simply assign each function to be n to the I for some value of I in this sum. So that's how you'd actually derive the rule I gave you the other day, which is pretty slick, right? So you can check out this proof. It's going to be in the notes. So you can find those notes in the so just check out the description to find where you can find those. I already talked about that before. And of course, that's everything. That's everything for this example. But yeah, no, so like there's this generalization. It's really slick. I've never really encountered this generalization documented like this. I think I'm one of the first that really properly presented this, at least for more of a computer science audience. Usually you only learn about each one of these separately, not them combined together like this. And I must stress that if you actually look at this proof, the way it works is that you would pick the constants in relation to the coefficients, and then you just pick n0. I believe, I'm tempted to say n0 is also 1. It is. So you'll find that the strategies that you've been aware of for polynomials actually can generalize even further. But yeah, you can check that out in the notes. It's on Patreon. But yeah, no, so are there any questions or anything? Let me just get that open there. It's fairly quiet here today. I know there's some people watching, kind of popping in and out. Some other people are just sticking around. Not too many questions. That's okay. But you'll find that this might be a very helpful resource if, say, for example, you're looking for a proof for a given big O property. I'm trying to give a good list of all of these. So if you find yourself needing to find them as a resource, then you have them here. So if anybody is ever asking, oh, well, how do you prove the transitive property or something like that? I'm going to include all of them. So any ones that I'm missing, if you want me to prove another one for you, just let me know. Let me know. I'll try to include it as well. Say either today or possibly in another session. So let's talk a little bit about this. I believe I only have 2 more proofs to go. At least I think. Yeah, I think it's only 2 more. It's 2 more. So let's talk a little bit about those. So because this one will require, again, a bit of space, I'm going to erase the boards here. And let me just get that out of the way, and then we'll get into this. Actually, let me erase over there first. So for anybody popping on in, I hope you're having a wonderful day so far. Hope you could consider supporting my work or following. We have a lot of fun here. Let's head on over here. Let's go over here. Okay, so let's I don't see any questions. Like I said, it's really quiet today. Maybe Tuesday today is rather a little bit different for a lot of people. I don't know. Either way, I know it's summertime too. I'm sure some people want to get out and try to do some fun stuff too. But either way, like I said before, this will be available afterwards. And also keep in mind that all the proofs separately will also get posted in their own separate compartments. So if you want to watch these afterwards, they're going to periodically come out over the next span of weeks, okay? So anyways, let's get to our next proof. So anyways, let's go through another rule that we have, or property for big O, is adding 2 functions of the same order produces a sum of the same order. So some people like to call this the sum rule because it's involving sums. But let me write out what that means. That was a little bit of a fun slant there. So if f is big O of h, so remember we're having another one of these conditional statements. So it means that we're going to have this and the following also satisfied, and g is big O of h, then it has to be that if both of those are true, then it has to be that f plus g is big O of h. So suppose I give you three arbitrary complexity functions, f, g, and h. If f is big O of h and g is big O of h, then you could say that the sum of f and g must also be big O of h. So you might say, Dan, we've seen a statement sort of like this before, but not entirely. It's now got two conditions here like this. So how can we use that? Well, let's first write down the game plan so we know the ultimate strategy for what we're going to do here. So that's usually a good place to start. So we understand the statement. Also, it's a good idea your reader has some idea what you're doing. To prove the claim, remember these are three arbitrary complexity functions. So I'm just going to avoid writing that here just because it just adds space here that we don't need to use. But if you find yourself really needing to see that, or say you need to write that out every time you're used to it, just do it. We determine constants. Right? We need to find those two constants, or we're going to find those two constants for the big O definition. C, which is a positive real number, and we have n0, which is a positive integer. Right? Such that the following is the case, such that for all n greater or equal to n0, it has to be that f of n is less than or equal to c times. Now, are we trying to prove c times g of n, or are we're trying to prove that f? So remember, we need to make sure we state clearly what we're actually trying to do. So it's very easy to fall into the trap of just writing out like what you're used to writing every single time for the big O definition. But remember, the claim isn't that. The claim is if we have those two things, then f of n plus g of n is less than or equal to c times h of n. That's what we're trying to prove given these two things. So you might say, Dan, what are you going to do here? Now, in a previous claim like this, like where we had some condition we can use, we would like to be able to invoke something here. Well, we have if f is big O of h and g is big O of h. We know both of those are big O of h, right? Well, let's just pull out their definitions, right? We're going to use existential instantiation to create names for those constants that exist for each one of these big O definition applications. So we're going to apply the definition of big O here. We're going to apply the definition of big O right here. And then we're going to kind of take them, give those constants names. Then we're going to try using them, okay? So both f is big O of h and g is big O of h, implying the following, right? Implying we have pairs of constants. I'm just going to list them all out together, and then I'll write out two inequalities for each. Well, one inequality for each, sorry. Implying there are constants. There are constants, C1 and C2, which they're going to be positive real constants, and N1, N2, which are going to be positive integers. So that the following is the case. So that f of n is less than or equal to c1 times h of n for all n greater or equal to n1. So far we have that, right? That's the first application right here, right? That's f is big O of h. This is what this says, is that we have c1 and n1 in relation to this inequality. F of n is less or equal to c1 times h of n. And now we have the other one. And g of n is less than or equal to c2 times h of n for all n greater or equal to n2, right? We have both of these at our disposal. So for sufficiently large values of integers, right, we have n1 and n2. For n1, you know that f of n is less than or equal to c1 times h of n, right? And we also know that for values n2 and greater, that g of n is less than or equal to c2 times h of n, right? So the intuition behind the sum rule is that, suppose I take a function, I don't know, let me just, gotta get it out of here. It takes a lot of force. Let's get it out of here. There we go. Now let's get this one open too. So I have two, suppose that these are two arbitrary complexity functions, f and g. So what the goal in our proof will be is, suppose that this is f and that's g. If I take these together, and suppose that this set over here, this bucket, is big O of h, it should be that if one of them is in big O of h and the other one is big O of h, it has to be that when I add them together, whatever the contents of these are, they should both together be able to, like if I took these, take a piece of let me just get some tape here. Let me just go grab that. Tape. Where would tape be when I want it? I'm finding tape, okay? Here's tape. I got tape. So suppose that I have these, suppose I have f and g. So if I sum both of them, if I sum up both of them, it should be that when I take them together, each one individually, actually, I think it needs more tape. Let's get some more tape on here. Let's get some more tape on here. Let's get some more on here. Okay, there we go. Definitely, now it's not going to move anywhere. So I have f and g, I've summed them together. The intuition about this statement is that it should be that when I sum the two together, they also should go into big O of h, regardless of what they are inside these magic boxes. So this one would just be f, this is g, or this is g, this is f. The point is that when I take them and sum them together, they better belong to the same set of complexity functions. So now I have these two inequalities. I'm going to employ something you should remind you of the max rule when we did that approach. Now I have two inequalities, but here's the thing. I know that they're true for only certain values of n1 and n2 and up. So I need to make sure that when I state this next part, I make sure that I state it for n that are sufficiently large. So I need to actually say what values those are. So this is actually how you might phrase this bucketing approach that we've been using. This is one way you can phrase something like this. By summing over both the inequalities. If you find yourself not satisfied with that description, you can always give names to the inequalities. Over both the inequalities. When n is greater or equal to the max of n1 and n2. So it's important that we have it where it's going to be at least n1, n2, right? Because remember, that first inequality was true for n is greater or equal to n1. The other one is true for n is greater or equal to n2, right? So if I make sure it's at least as big as the larger of the two, then we're okay, right? So let me just write out here when this is the case. The inequality, we'll say when this is the case. Let's just keep it short. I don't want to get to too many things. Now things are going wonderful. Going wonderful. Let's see here. N1, N2. We have, now I'm just going to sum over the two, one for F, one for G. Now I'm going to write their right-hand sides on this side here. So that was C1 times H of N on the first inequality, one relating to F of N. The second one involved G of N. Hopefully you have C1 times this, C2 times this, but this is the same among both of them. So now I'm just going to have it where it's times H of N. But if you look very carefully at this, less than or equal to C1 times times H of N. Okay, you could just make this C by selecting. Then we have that F of N plus G of N is less than or equal to C times H of N. And this holds for all n greater or equal to n0. So now I just need to pull out the definition of big O and then we're done this proof. Isn't that nice? So now I have the two constants. Therefore, by the definition of big O, we know that F plus G is big O of H. And that completes the proof. That completes the proof. Isn't that nice? So just to be clear, so what this is saying is that if you know that one complexity function is big O of one complexity function, and the other one is big O of the same complexity function, when you add the two, it should end up being that same one. So just like I had here, where I had F and G together, where I sum them together, they belong in the same bucket as if I put them separately. They should belong in the same one if they both belong to big O of H. It's pretty sweet, right? So let me get the chat going here. There we go. Hello, Master Dre. How are you doing? Yes, it did. It did. You missed me taping stuff. I took out the tape. I was looking for my painter's tape. I was gonna go, and I had to get some Scotch tape. Just gonna move these over. Believe it or not, we only got one more proof to go through today, but no, it's been fairly quiet here today so far. It's actually kind of funny. For missing stuff, but Dan, I'm here right now, at least somewhat. Yeah. Their promise with me. Awesome. Okay. Okay, that's good. That's good. I'm glad to hear that. I'm glad to hear that. I like it when people keep their promises with people. That is something that is admirable. Most certainly. But yeah, no. We're actually going to go through one more proof here. And then I think that'll cut it for today. But all the proofs I've gone through so far, if you ever find yourself looking like, hey, look, I'm taking an undergrad class in like data structures and algorithms or anything like that, knowing all of these will ace you any kind of exercise when you're coming down to just basic properties. So sometimes people ask you to prove some of these. I've laid out most of them. There's even more than just these, and there's generalizations of them beyond this. But most certainly you can keep going with them. There's many, many more properties. I'm just giving some of the basic ones. I don't claim that you'll ace every one, but most certainly I'm laying out a lot of the fundamentals. But we only got one more I'm going to cover here. If there's more properties that come up, well, certainly I'll do it in another session. But we got one more to go through, and it will adapt the same kind of idea that we used here Actually, no, we have two more. I was mistaken. It's because these next two properties actually employ the same argument, the same kind of setup. So that's why usually I show you one of them and then I'll show you the other one, because the way their proofs work are almost, yeah, they're almost they're pretty similar. So if you've gotten a feel for this idea that if I have some preliminary information I can use those pieces in my proof to make arguments that lead me to the conclusion I'm trying to argue for. And the other thing that sometimes people forget about is that also we're trying to prove these things for arbitrary complexity functions. So you can always plug in any one complexity functions you like, as long as they meet the conditions of the statement. Like they could be n squared, they could be log n, they could be whatever you want them to be, as long as they're complexity functions, and they should hold. But the thing is, our proofs, we cannot just simply take special cases and say that's good enough. We need to do better than that. We need to do better. So let's so I'm thinking we'll go to our next two examples. If there's any questions between the two, what I'll do is I'll go through this example, and if there's more questions after it, we'll certainly go through it, okay? So let me just get in on this. But don't worry, it's all good. So here's the next one. And now I've given names for some of these rules, like max rule, sum rule. This is another one. It's called the product rule of big O. So some people will call it this. And it goes like this. And I warn you in advance, it's going to have a little bit more going on with the statement, but I assure you, the way that the statement gets set up makes it really easy to prove. At least I think it is. Or at least I hope to convince you that the way we ration through the reasoning is actually really nice. So at first it's going to look like there's a lot of bookkeeping. Definitely not as much as most cases we've had it. So we're going to have, there's going to be 4 complexity functions, 4 arbitrary ones. Let there be 4 complexity functions. So again, you could think of these like an n and an n squared, an n cubed, a log base 2 of n, 2n, whatever you'd like. Let there be 4 complexity functions. Functions, we have f1, we have f2, and we have g1, and we have g2. Sorry, I was about to put the 2 inside of there. So we have f1, f2, g1, and g2. So these are 4 functions. So if I know if f1 is big O of g1, and f2 is big O of g2, you might guess quite quickly where this is going if I call it the product rule. Then it has to be when I take the product of f1 and f2, there has to be big O of g1 times g2. Then f1 times f2 is big O of g1 times g2. So like I said, it's a lot of busy work kind of getting this all set up. But once you have this in place, it's actually, believe it or not, the setup for this proof is going to remind you a little bit of what we did in some previous examples. So here we go. And here's the intuition behind this. Or at least this is one intuition you can use. We know f1 is big O of g1. We know f2 is big O of g2. We have these 2 things that we can use. So it means we're going to get constants for each one of them. We're going to use what we called existential instantiation. So this statement involves the existence of 2 constants. That's why our definition works. So that means we can actually give those names, and we can use those variables, which are constants, right? We call them constants just for the sake of clarity. So I have names for those. And then I'm going to just find a way to mesh them together so that I can form a statement that gives me this. That's going to be what we're going to try doing. But you might ask, Dan, why would we care about this product rule? Well, suppose, for example, I'm going to give you a setting, for example, that comes more from programming. So, for example, suppose that G1 and G2 are total numbers of operations that happen. One for, say, involving F, so it relates to F1, and the other one is involving F2 in relation to G2. Suppose you have a nested loop. So you have like a for loop or a while loop, and then inside there you have another for loop and while loop. Now suppose that the number of operations that happen is F1 inside the innermost loop, and the outermost loop performs without consideration of what's happening in the innermost loop. So for example, say the innermost loop happens, say, n times, and say the outermost loop, the for loop, performs n iterations or something like that. Well, if you count up the number of operations that happen in the innermost loop, each one happens for each iteration of the outermost loop. Well, what does that count up to? It's a product like this. So if you figure out the big O for the innermost loop, and you figure out the big O for everything outside of that based on how many times it happens, like say, for example, you know, like the outermost loop, it's like a for loop that does n iterations, for example. Then it's saying that, okay, if you had big O many this operations, then you have big O many operations of the outermost part, then you can take the product of the two. And it's really nice. So this is actually a nice general rule that you can use. Sometimes it's helpful when you want to quickly do a quick analysis. So just be clear what I mean by this. So say if you have a for loop and then another for loop, and there's some stuff that happens inside of here. And say this happens n times. And this happens, say, n times, just as an example. And say all the work that happens with this innermost part is, say, big O of n. And you know that this happens, this outermost for loop happens big O of n times. Well, because it's n, right? N is big O of n. Well, if I want to know how many operations happen in total over all of this, well, it's the product of these, because for each iteration of this, you do this, right? But I know how many operations happen in total is G1, and the other one, sorry, big O of G1 for the innermost part, and this is big O of G2 for the outermost part. So in this case, G1 and G2 are both n, and F1 and F2 are something like n. But yeah, so you can see that this manifests itself into some pretty hard and fast little rules that sometimes you learn in some introductory computer science classes, at least when you start talking about big O. But anyways, let's get into the proof, okay? So we're not going to worry so much about that. I just want to show you how you actually prove this. Remember, this is a statement about any two complexity functions. I'm just giving you an example over there of how this might manifest itself when you're doing time complexity analysis. So like when you analyze the running time of the algorithm. So anyways, so as per usual, we need to say what we're going to do, right? We need to give a game plan. So when somebody picks up your proof, they're like, what's happening? Somebody help! Help! They aren't doing that. In order to prove the claim, we find constants. So we find those two constants. Remember the two constants? So we usually call them C and N0. C and N0. Remember, C is a positive real number, N0 is a positive integer. And such that for all n greater or equal to N0, we can say that F1 of n times F2 of n is less than or equal to C times G1 of n times G2 of n. The statement makes sense, everybody, right? So this is just us trying to prove this claim. But notice that I have this and have that at my disposal I can use in my proof, which is what we're going to use next. I'm just going to switch markers here. Cross my fingers, this one's better. So let's get in on this. if F1, G1, and F is big O, then, like definitions, right? This means this of constants, a C and an N0, but we got to give them different names so we don't confuse them with those ones. Different variable names for things that you already have names for those things. It reduces the ambiguity you might have when people are trying to understand what you're trying to say. Then by the definition of big O, because this is because of the definition of big O, we get the following. So let's head on over here. Come on over, okay? let's go over here. So we get the following. By the definition of big O, there exists 1 times G1 of n. And this has to be true for all n greater or equal to n1 by the definition of big O, right? And we have that F2 of n is less than or equal to C2 times G2 of n for all n greater or equal to n2, right? So both of these are true. So I already see that. So all I've done is I pulled out the definition of big O twice, and I'm just spilling out in a nice kind of uniform way each part of me using the definition of big O. So now I have those two things. I have these two inequalities. Akin to an example we've seen before, I'm going to try to pick it so that n is going to be at least n1 and n2, so that both of these are true. But here's the catch. Here's the catch. I want to make something that looks like F1 times F2 on the left-hand side. Well, does anybody see anything I can do here to make that happen? Well, before we usually just summed over the inequalities, can I multiply? Sure, I can multiply. Let's try multiplying, okay? So watch this. Then I'm going to pick N0 up front, just because I feel like it adds a little bit of spice to the discussion here. By selecting N0 is equal to the max. So remember, max just simply means I take the larger of the two values. So I take the larger of N1, N2, and I observe by multiplying. So we'll say multiplying over. We're taking the product over. Multiplying over the two above inequalities. These two above inequalities for all n greater or equal to n0, because I made n0 big enough, so I could just use these two facts. I have these two now because n0 is big enough. Then I'm going to just f1 of n times f2 of n. Well, if I take the product of these, then I have to take the product of both sides, right? So I have f1 times f2, and I have c1 times g1 times c2 times g2, all on the right-hand side. So I have the first term, c1 times g1, and this is multiplied by c2 times g2. But if you rearrange this, akin to one of our other examples, you're going to see that I could take c1 times c2, because remember, I have c1 times g1 times c2 times g2. I can always permute products like this, because they're just numbers at the end of the day. When I look at the outputs of these, the order here does not matter. I can just commute or permute, if you would like to call them that. I can take these two. I'm just going to pull them out front like this. Then I have g1 times g2. But look at this. Look at this. Now I have c1 times c2 times this thing. This is what I wanted, right? f1 times f2 is less than or equal to some constant times g1 times g2, right? But what's this? Well, if I make this c, we're done, right? So choose, well, let me put a period at the end of this. So choose c is equal to c1 times c2. Therefore, Therefore, by the definition of big O, we can say that F1 times F2 is in fact big O of G1 times G2 all together in there in the big O. And we're done. End of proof. Piece of cake, right? So you'll notice I'm just using the same types of bucketing strategies. And that's really it. That's really it. It's really nice. Just instead of doing it over a sum, we do it over a product. So are there any questions or anything like that? Or was that pretty much okay? It's a little tricky. It's got a lot of bookkeeping because there's a bunch of functions. But you're going to find that a lot of the last couple, well, the previous one, this one, and the last one we're going to do, which I would argue is probably one of the more important ones. I'll actually give a couple of examples of why you might care about this last property in combination with a couple of things. I'll give that in a little bit. There's this thing called the transitive property called the transitivity property. Where if you want to go from one big, like if you have a statement about big O of one function and you know that the function inside your big O actually relates to another function in terms of big O, then you can actually just bridge the gap completely. I'll give you a couple of examples of how you could use this in some sense that actually involves every one of the proofs we've done. So I'll show you an example of how you could use that property. But yeah. So you can see that a lot of these sort of manifest themselves when you actually talk about like an actual algorithm. Because the main reason why is because when you're counting up the operations that happen from a given algorithm, if you think about like a computer program, you count up the number of instructions that occur. If you do it in a way that's a machine independent way, so for example, you're counting up all your additions, your assignments, your like how many times these happen with respect to your given input, which scales based on the size of the input. It's not very much a surprise that that intuition should pop up in some of these rules, because the way the rules are formulated are meant to be sort of encapsulating some of these common techniques or patterns. So it's not very much a surprise that they should manifest in a couple different places. That's just my opinion on it, but I don't usually talk about my opinion, but most certainly I think that each one of these rules sort of has their own intuitive counterpart if you actually think about it from an analysis standpoint. And so a lot of these turn into very basic rules that you can use. So for example, like the max rule, like I talked about that earlier, where if you have like the sum of like two functions, whatever the larger of the two functions is, you write that in the big O. And that's pretty much naturally how it plays out. Just same idea with like the product, like we talked about nested loops, for example, as an example where this product rule pops up. So like they manifest themselves in some pretty interesting places, and these give you some nice shortcuts if you find yourself looking for a good shortcut that isn't, and it really isn't like a bad thing to shortcut here. It's just true. Now, the natural question is do you want to use that rule? That's a real fun kicker, because sometimes when you're doing things like, oh, like I have a nested loop like this, sure. In this case, it seems nice and straightforward to be like, oh, it's the product of the two, and I can count up how many there are like that. Most certainly. And if you want to get a big O property that gives you a shortcut to get there, you can use this product rule over here. If you count up the number of things that happen inside the loop and how many times the outermost loop happens, piece of cake, right? You can say that this will give you the result at the end of the day that's big O of n squared. But most certainly the big problem here is that, like, okay, well, what if the algorithm is actually fairly sophisticated and it actually doesn't really account for that? So big O is an asymptotic upper bound. So if you might be overcounting, that's what I'm saying, is sometimes you do run into cases where overcounting actually happens. And you may actually have a complexity function that overcounts the number of operations in your algorithm. And that has nothing to do with big O, really. Big O will still be, it'll still be true if you're overcounting it. It'll be an asymptotic upper bound on the time complexity or the complexity, the number of resources your algorithm is going to need. But most certainly it may not be tight. That's what I'm getting at. But these are two separate things. Counting the operations and all that stuff, that's one activity. Determining the big O, that's another activity. We're mostly looking at the latter one. But I just do find it interesting when these things pop up in these rules like this. I like to think of them as little toolkits if you find yourself just looking for hard and fast rules. Especially if you're just looking for a big O. That's just kind of what you want. It's just the big O. Give me it. And these give you these proofs tell you why they're true. But yeah, so why don't we do one more? We got one last one. It's the transitive property. So hopefully you're a little excited for that. I'm going to kind of spoil it for you while I'm erasing the board here. Is that it's going to be somewhat familiar to you if you followed the product rule. It's actually a simpler proof than the product rule one, but I'd argue it's kind of I argue that some parts of it are a little slicker, but it's using the same kind of approach where we had the inequalities. We derived those using the definition of big O, and then we brought those together. But we're going to do it in a somewhat different way for the transitivity property of big O. But I promise I'll give you an example of how the transitive property can be used. A very common, you might ask, Dan, why would we need it? Is that you don't need it. It's just, it's a nice property big O has. It has nothing to do with people's utility for things. That's one thing that often and I will say that a lot of computer science people often fall into the trap of is thinking of everything in terms of, do I need it or can I use it? Thinking in very utilitarian terms. Some things are true for the sake of. They don't have to serve somebody's purpose. So anyways, let me just get this sucker over here. Whoops. Oh no, it didn't fade properly. Anyways, let's get in on this. So the next property I'm going to prove for you is the transitivity property. So it's the transitivity of big O. Some people call this the transitive property, or say big O is transitive. And here's the way this works. And this is a common property that a lot of different mathematical objects may have. Not all of them, but some of them do. But this is how you would state it for big O. So suppose I give you three arbitrary complexity functions, f, g, and h. Here's the statement. If f is big O of g, and g is big O of h, then you can say that f is big O of h. That's what the statement is, and this is what we're going to prove. You can see quite quickly that we have a conditional statement. So you have if this and this are true, then it has to follow that f is big O of h. One way you can look at the transitive properties, you're cutting out the middleman. So notice that I have involving f and g. So what I'm doing is I'm going to cut out the g part. So that's the intuition behind this, is that for the way transitivity works, is that I should be able to talk about f and h, and I'm going to cut out g, the middleman in here. So I'll give you an example of how you might apply this transitive property after the proof. So let's get into this proof. As per usual, I have to lay out the game plan, everybody. So here's the proof. We have to find the constants, right? We find constants. One is a positive real number. The other is the positive integer, n0. So I have c and n0, where it has to be that f of n is less than or equal to c times h of n for all n greater or equal to n0. Thought I'd write it a little differently here. So let's get in on this. So we know that f is big O of g, and we know g is big O of h, so we're just going to invoke and use existential instantiation to make that happen, okay? So we're going to come up with names for those constants. Since f is big O of g, and g is big O of h, there exists constants C1, C2, which are going to be positive real numbers. So I'm just going to pair them up based on this one involving so C1 is going to involve the first big O statement. C2 is going to involve the second big O statement. C1 and C2 and N1, N2 such that both f of n is less than or equal to C1 times G of n, right? That comes from the first application of the big O definition. For all n greater or equal to n1. And we also have that G of n is less than or equal to C2 times H of n for all n greater or equal to n2, right? So what I'm going to do is akin to one of my other examples. I'm just going to pick n0 right away because I would like to pick n0 such that this is true and this is true. Both of these inequalities are true. You're going to see why in a moment. Choose n0 is going to be the max of n1 and n2. Remember, this just takes the larger of the two numbers and it sets that to be n0. Then we find n0, well, let's find the constant. Remember, we have to find the constant c. I haven't done it this way in quite a while. We need to find the constant c. So notice, usually we find n0 next. I'm going to find c next. I thought I'd give us an example where we're doing it a little differently. So that f of n is less than or equal to c times h of n for all n greater or equal to n0. So now we have what we need here. So now I'm going to take the two inequalities I have over here. We're going to add over both of them. Or am I? Should I do that? Probably not. No. In our previous examples, we would do that, but I don't want actually a statement that involves f plus g, right? We want something involving f and h, right? But here's the thing. Wait. Let's go back over here, camera. Come back. Go this way. Go this way. This way. I want to point out something that's rather important for how we're going to play this out, okay? So let's see here. Keep going, camera. Keep going. Okay, I think okay, there we go. So notice here, so I want you to notice, we're not going to add the inequalities, which is what we've done many, many times. We're not going to multiply them. Instead, what we're going to do is watch this. I want to say something about f and h. But notice that in the middle here, so and for this inequality, I have the c1 times g of n. Do you see how I can try to take this inequality and combine it with this one, such that this part here, it goes right here. So I want to like sandwich, I want to be able to put this in the middle between here. But to do this, I would have to take c1 and multiply it to both sides of this inequality. Then you can see it flows all the way through. Do you see that? So that's what I'm going to do, is I'm going to try to bridge the two inequalities. So using the above inequalities, which was over there, above is now left, okay, everybody? Using the previous inequalities, observe that for all n greater or equal to n0, because remember, I've picked n0 already. And we know both of those inequalities are going to be true for these values, well, for the value I picked for n0, right? So for n0 and greater, sorry, I'm getting very excited about what we're going to do here. So I know that this is C1 is less than or equal to C1 times G of n, right? And now what I'm going to do is I know G of n is less than or equal to C2 times H of n. So I'm just going to drag this C1 along, take it for the ride. Right? This is perfectly valid because C1 is a positive real constant. And next, I'm just going to put C1 and C2 together. And what's this? Well, you could pick this to be C, right? So I'm just going to select C to be equal to C1 times C2. Therefore, by the definition of big O, F is big O of H. And we're done, right? Because that's what this states. And that's how we can prove the transitive property. Now we know that big O has the transitivity property. So I thought I'll give you just one example of how you might use this. Now, in a previous session, I showed you how you can prove, say something like n to the k is big O of n to the k, right? In fact, I showed you that if you had a polynomial, like if I had a polynomial, and the way I defined it was eventually this had the most dominant term in it was going to be an n to the k. It had like n to the k times a coefficient plus n to the k minus 1 times the coefficient and so on. We showed that this is true. In another session, it was the previous one to this one, I showed you that n to the k is actually big O of n to the k plus epsilon, where epsilon is a positive real constant. So, if you use the transitive property, what I could conclude, and keep in mind that this exponent will be potentially a fractional or even a real number. It will be something, it might be something else. It's completely not like the polynomial rule we had earlier on in earlier sessions. What I could do is, well, this is F, that's G, this is H. So from this, I can conclude that given a polynomial, as per the way I had it in the previous session, you can conclude it's n to the power of k plus epsilon, where this is any positive real constant. So it means that you can show that any polynomial with its dominant term is n to the k. You can show that it's big O of n to the k plus epsilon. So for example, if you want it to be, like say if you found out that this polynomial here ends up being something like n squared plus n or something like that, you can conclude that this, if for whatever epsilon you want, you can show that this is 2 plus epsilon. So if you want to make that 0.5, you can show this actually will give you the ability to say, well, at least from the techniques I've shown you, that n squared plus n is big O of n to the 2.5, for example. So this is actually one way you can generalize this property. Is that nice? So this is actually one way you can bridge over fractional exponents or even real valued exponents. So the transitive property actually gives you this ability in a very nice, slick way, like this. So that's how I could bring together a couple of things I showed you with the transitive property. But yeah, isn't that neat? So let's head back over here onto the chat here. But yeah, that's the last proof I was going to show you here today. I heard a couple of fun dings going on here, so I'm really excited to see that. But yeah, no, if you're watching this, it's always a pleasure, as per usual. We have a good time here. I've already walked through all of the main properties that big O has in their complete proofs. I will be talking about more big O properties probably in the future as well. But keep in mind that all these will be separately put out, but this video, along with the live stream that we've talked about, will become available also afterwards. So if you find yourself watching this right now and you're like, hey, look, I want to watch this whole thing, this stream will not go anywhere, okay? At least on YouTube, it won't. But I will be cutting it up into nicer bite-sized pieces so that you can review them in your own time if you'd like as well. But yeah, no, hope you're having a wonderful day. I seen a couple of things going on in the chat, and I also seen a couple of dings coming off left and right, which is pretty awesome. I'm excited to see that. But yeah, no, so this will provide you a lot of the basic artillery if you find yourself analyzing algorithms and you find yourself wanting some quick rules to, say, for example, dropping those constants. I showed you one example where how that manifests in a big O proof. I also showed you how if you have nested, like a nested control structure, how you can easily deduce the big O from that. But remember, in that case, it may as well you're just going to be counting up the operations anyways. It's more, the product rule is really helpful when you have only one thing that's happening and you know the time complexity of that in terms of big O, and then you know how many times it's going to happen involves the other function. You take the product of that, you're okay. Just be warned, if it is a rather sophisticated algorithm, it might overcount. But that's okay in big O. Technically speaking, it is an asymptotic upper bound. It might overcount, but using the M word, the maths, the mayonnaise, it makes a really good sandwich. It's still true. It just may not be as accurate as you might like it to be. But yeah, no. Are there any other questions or anything like that? I'm really happy to answer any questions. If anyone has any fun things they want to chat about, that's also cool too. I'll stick around here a little longer as we're kind of just chilling out here. But yeah, that's all the examples I was going to cover here, at least when it comes to things I've prepared. But yeah, no. So far we've done, we did the fundamentals. So we had a previous session on that. We talked about smoothness. So, for example, if you ever wonder how you can get away with, for example, presuming that the input is like a power of 2, for example, how do you generalize your results anyways? That's smoothness for you. A lot of complexity functions computer scientists study or include in their research typically will fall into this domain. Not all of them, but most certainly many of them. But in addition to this, you'll also have cases where, for example, you have it where you have these cases where you have all these basic properties. And these are nice to know about big O, because very often you would like to have some way you can generalize your results without having to prove each one separately. Or you want a simple blueprint for how you can prove any one of these kind of claims where you just substitute in your complexity functions. They all serve as blueprints to allow that to happen. So you can almost look at them like patterns you can easily apply to your own claims. But yeah, so just give you a flavor for what's coming up when it comes to Big O Bootcamp specifically. I might be switching over to talking more about data structures and algorithms. I might try to mix it up a little bit every other week or something like that. If not, I might be also doing more lessons too. We will see. We will see. But my next Big O Bootcamp session will be on logarithms and how we can use that to capture Big O claims for logarithms and exponential functions as well. I am planning to do another session also on recurrence relations, because very often describing the running times of algorithms as recursive functions, well, when I'm talking about recursive, I'm talking about recurrence relations. There's another technical term in computer science and mathematical logic called the recursive function. That's a whole other thing. I'm not talking about that. Talking about when a function is described in terms of itself, just very basic kind of counting functions. We're not talking about anything more sophisticated than that. I want to do a basic session on how you can deal with linear versions of these. So some basic techniques for counting for those, and some concepts like recursion trees. And I would like to eventually build up to things like the master theorem in relation to this, and give you actually the proof for at least one version of the master theorem. And likewise, another session I have in mind involves, so the recurrence relations, that's something actually I promised at least a year ago. That was one of the things I was going to do. I also have to do a session on big theta, big omega, and little o and little omega, those different other asymptotic notations. I will be doing another session on that. I'm not sure what order each of these will be in, but most certainly it will be at least those three. Then on top of that, I plan to cover maybe a couple other things such as different variants of big O notation. For example, you may know of a different definition for big O, and I'll talk about different ways you can restrict the complexity function definition. So for example, in ours, we presume the function is non-negative, meaning that it never was allowed to take on a negative value. This makes absolute sense in computer science. The complexity function would make absolutely no sense to be negative at any point. It just doesn't make any sense. But suppose that you want to have it where it's allowed to become negative at some points. There's ways to easily characterize this such that you can adapt any of the techniques I've shown you here. Likewise, if you want to have it where the function has a certain behavior, I want to talk about some of those things. In addition to this, I also plan to talk about multiple variable versions of big O notation. So for example, very often when people study algorithms, very often you are used to expressing big O notation with multiple variables. So for example, if you're studying like graph theory, you're very used to having it where you have, when you're doing like graph traversal algorithms, you may have things like big O of n plus m. I would like to give you some formal underpinning to allow you to prove claims like this about some complexity function without having to appeal to simple usage rules. So if you really want to like dig in and play around with it more formally, I will give you options for that as well. Believe it or not, every technique I've shown you is really not that much different from doing things with multiple variables. But yeah, so there's a bunch of things we're going to do with Big O Bootcamp. As I mentioned earlier, the goal with this project is going to make it so that there's an accessible way to learn all of these different techniques so that, for example, you're not left in the dirt about why certain claims are true. And you also have examples that allow you to ace those Big O exercises, okay? So I'm trying to give you resources such that, say if your computer science prof is really not the greatest at teaching this stuff, you'll have an option out there. And also, on the same time, if they give you very loosey-goosey exercises that might be much more common than your professor's letting on, then these will exist as additional tools that you could use. Eventually, this is going to be compiled into one book, and I'm going to be trying to make this book fairly affordable for anybody. So that if you want to study Big O notation or have a nice little handbook that you can go to find any one of those proofs or find lots of examples, I'm planning to put a comprehensive guide together on this. Now, it won't cover necessarily everything. So for example, this is targeted directly at computer science students. So if you're interested in a lot of what I'm talking about here, for example, I talk about complexity functions in the context of computer science. So for example, we measure the functions based on running times of algorithms, for example, or the amount of space you use. So some definitions don't apply, say, in the same way that they might for analytical number theory, which is another way you can use Big O notation. So at some point, I want to give a little bit of treatment to this idea, but it's not the main focus here. But I'm trying to come up with a nice ultimate guide, whether it be for fundamentals, but also for a lot of exercises. So if you find yourself lost on this topic, there's lots of resources that are going to be available to you, and I'm going to try to make them available like this. But yeah, so do consider checking these things out. If you're not subscribed yet, do check out things on the Twitch. We got the YouTube here. We got Facebook. We're all live. I'm live on all three of these right now. If you're curious, it's right now we're having ourselves a good time. But yeah, do follow. Tell your friends. So if you're, say, for example, a computer science student, or you're interested in computer science, or you're just interested in hearing me chat about all sorts of fun stuff, some abstract stuff, tell your friends to come on out. Everybody is welcome, okay? So I'm going to stop right here. I think this is a perfect place for me to stop. I'm going to say thank you so much for coming on by. It was a pleasure, as usual. And I guess I could take my hat off now. So I'll say thank you so much, everybody, and have yourself a beautiful day. I'll see you later.